Somebody having the little bells that we
Yeah.
have to play.
That's something from St. Air.
We should get those. No, not that one. Or maybe, is it like that show or the dog or something that has like the pleasant chimes?
But for time.
It goes like bong.
Silence
Silence
has
has that.
a like bring out that kind of.
Yeah, no, that's not pleasant at all. This is like a nice soft ringing.
Oh, yeah.
Okay, so now that you've heard of Haley's work from all sorts of people, you get a chance to hear about it from Haley herself.
Thank you. Yeah, okay. So yeah, I'll just talk about this project that Valentine and I have been working on lately, and it's given some connections between witness encryption and NP-hardness. So we've been at this workshop for a few days now. Yes.
Do you have a microphone?
I can try to, I'll speak louder. Okay, yeah. I'll try. Okay, so we've been here a while and we know that cryptography and learning theory are not really two unrelated subjects under the umbrella of computer science theory, but they're really like two sides of the same coin. And they're kind of working against each other. Even in 1984, when Valiant introduced PAC learning, he already realized that if it could be done efficiently, it would preclude like private key encryption, like PRS. And lots of different relationships between different types of cryptography and worst case, average case, easiness of PAC learning have been given in the literature and talked about this week. Okay, but I'm not really going to talk about that right now. I'm kind of going to talk about versions of these questions that have like more of the structure of NP languages kind of baked into them. Okay, so in cryptography, I'll be talking about witness encryption. So is it possible to encrypt a secret bit with security being contingent on the ability to provide a witness for an instance of an NP language? And then in learning theory, I'll be talking specifically about NP-hardness of learning. So is there a reduction, say, from SAT to a learning problem that's like preserving membership for correctness? So a little bit of background. I don't remember if we saw this already, but just to define agnostic PAC learning, you can think of it as an agnostic PAC learner is given access to an example oracle, distribution E over string label pairs, X comma B. And I guess she doesn't like to talk that much and she just gives you one data point at a time. And then the goal of an agnostic learner for a concept class C is to produce a hypothesis H, having agreement over that distribution E that's like almost as good as the best function that belongs to C. And just to note that this distribution E, it might not even represent a function in the agnostic case. Okay, and then you can refine the definition further. So proper means that H needs to belong to C. Improper means there's no restriction on the complexity of H. And then you can talk about like weakly proper or semi-proper settings where there's some restriction on H, but maybe not as like tight as having to belong to C.
Well, like maybe be like a function of several functions in C or something like that. Example of
That's a good example. The one example I'm thinking of is like learn with respect to size S by size S squared.
Okay.
Okay, so I'll be talking about reductions to agnostic PAC learning. And maybe it's not immediately clear what that's going to be. Like for one thing, it's not a decision problem. And indeed, there are a number of different ways that you could think about this. So I'll be looking at a couple definitions given in this paper from Applebaum, Barak, and Zhao. So they talk about at least two different types of reductions to PAC learning, or agnostic PAC learning. Okay, so this is the first type. It's a randomized, non-adaptive reduction to agnostic PAC learning over a distribution sampleable by poly-size circuits. So what is that? It's this randomized machine R, takes like say an instance of SAT as input, and then it makes some oracle queries to an oracle that it presumes to be an agnostic PAC learner. Okay, and what are those queries? Those are circuits sampling the sort of distributions E that we talked about over example label pairs. So it's querying the distributions to the learner, and then it expects to get back a hypothesis represented as a circuit that has like nearly best possible agreement over E. Okay, and then it can look at the hypothesis and do whatever it wants with it, and it's supposed to decide membership in SAT. Okay, and the authors show in the paper, one of their main theorems is that if this type of reduction exists and it works in an improper setting, then you can rule out Passieland. Okay, and then the second type of reduction to learning that they talk about is going to be kind of much more limited in its use of the learning oracle. So it's kind of only using the oracle to make a decision of whether or not there is a small circuit like somewhat consistent with E. Okay, and then you can define this decision problem to formalize that. And in their paper, they call it the computational gap learning problem. So CGL, and it gets these parameters, S1, S2, and epsilon. And then the input to this problem is just, again, one of those poly-size circuits, sampling a distribution E over example label pairs. E is a yes instance of CGL if there exists a circuit of size S1 that's perfectly consistent over E. And then E is no instance if for every circuit of size S2, the circuit can only get epsilon advantage over E. Okay. And they show that if this type of reduction exists, and also it's a deterministic many one reduction, then NP has statistical zero knowledge arguments. Okay, now I need a slide about when.
So just draw a graph, or is it still going to be treated as like 1 minus epsilon there?
Yeah, I need to think about it honestly, but you may not need such a strong graph.
For conclusion, is this true? Like NP in statistical zero argument? Or at least kind of, is like something impossible, or is it actually believe that? Because this argument is easier for. Okay. So I see that's argument.
So defining witness encryption, it's a pair of algorithms, ENC and DEC, and ENC is randomized, DEC is deterministic. And the idea is that if I want to encrypt something, I need to do it with respect to an instance of an NP language. Okay, so if I want to encrypt a secret bit B, I do it along with an instance Z, and I use ENC to produce a ciphertext. And I send the ciphertext out to everybody, and it's guaranteed that anybody who can produce a witness proving that Z belongs to L will be able to recover the secret bit using decryption. Okay, so that's the correctness guarantee of witness encryption. And then the security guarantee says that if Z does not belong to L, then encryptions of 0 and 1 are going to be computationally indistinguishable. Okay, and then you can distinguish like security against uniform or non-uniform adversaries. Okay, so here's the first sort of equivalence we can state. We can say that non-uniformly secure witness encryption exists for NP-hard languages, if and only if CGL is NP-hard under what we're calling a half-Levin reduction. Okay, so more on half-Levin reductions later, but just to be a bit more precise about the parameters. So like the S1 parameter of CGL is going to kind of correspond to the running time of the witness encryption scheme and decryption in particular. And then the S2 and epsilon parameters will correspond to the security of the witness encryption scheme. So in particular, if you want full-fledged like cryptographic P/poly secure witness encryption, you'll need a single reduction that works for all polynomials S2 and all inverse polynomials epsilon. I'm kind of getting ahead of myself, but right, what is a half-Levin reduction? It's just half of a Levin reduction. Okay? It might be 2/3. It depends how you're counting. Okay, but it's just a pair of machines, R and R sub wit. So R is a deterministic many-one reduction, and R sub wit is like mapping witnesses for L1 to witnesses for L2. And then we don't need the third machine that you normally get an 11 reduction mapping L2 witnesses back to L1 witnesses.
Just trying to figure out which way you have which half you have.
Okay, yeah, so if X is an instance of L1 and we have a witness for that, then R sub wit is going to map the L1 witness to a witness for R of X being an L2.
So usually, like when you're doing reductions between search problems, you would actually want the other half to be algorithmic, right? Because you want to like solve the search problem for L2 and then convert it back to L1. So this is kind of the reverse half.
Okay, yeah.
Or that.
Yeah, I think that's right.
Okay.
Okay, so yeah, the statement I gave, I don't know if you find it surprising or not, but it has the proof is like extremely straightforward. Okay, so I'll just say it now. Here's one direction. So let's assume that witness encryption exists, and let's use it to build a half-Levin reduction from SAT to CGL. What does the reduction do? It takes an instance phi and maps it to the following instance E of CGL. Okay, what does E do? It just picks a secret bit B uniformly at random, and then it encodes B using phi. Okay, and then it just outputs the ciphertext along with the secret bit. So that's the whole, it's like the simplest construction you could think of, right? Just random bit ciphertext pairs.
So an instance of CGL is a distribution.
Represented as a sampling circuit. Yes. So let's argue that this is correct. What if I is a yes instance of SAT? Alpha is a satisfying assignment. We need to show that E is the yes instance of CGL. We need to show that there's a small circuit consistent with it. What's that circuit going to be? Of course, it's just going to be the decryption algorithm with phi and alpha hardwired into it. Right? So by the correctness of witness encryption, we know that no matter what B was, if we get the ciphertext of it, we'll be able to recover it. Okay, so there's DEC is the small circuit and it's a yes instance. And just to note that it is indeed a half-Levin reduction because we can construct this circuit efficiently given phi and alpha. And what if phi is unsatisfiable? What if E is, however, not a no instance of CGL? What does that mean? It means that there's a small circuit C that can look at an encoding of a random bit and more often than not tell you what the bit was. So that's bad, and that's going to be violating security of witness encryption.
That you only need, so the security is usually with respect to non-negligible, so you just want an absolute to be like likely and all like.
Yeah, exactly. Yeah, you can do this with a fixed epsilon, or you can say that if for any epsilon this happens, then
Fixed epsilon, yeah, you can do it like non-negligible.
Yeah.
Non-negligible.
so if this happens for any inverse polynomial, it'll break witness encryption. What time did it start, by the way?
Give me the
15, okay. Okay, so this is the other direction. I'll go through it really quickly. How do we build a witness encryption scheme out of a half-Levin reduction? It's just as simple as the last direction. So encryption is gonna basically run the reduction to produce an instance of CGL, sample something from CGL, and then output the string and the secret bit XORed with the label. Decryption is gonna run the witness part of the reduction to produce a circuit C that is like perfectly consistent with E. And then it can run C on the X like string part of the output and get back the secret bit. Okay, so I won't go through security, but it's expected. Okay, so you might also be interested in a situation where witness encryption is possible, but it's only secure against uniform adversaries. So we can also say something here. It's going to be equivalent to a BPP black box half-Levin reduction to a search version of CGL. Okay, so a little bit to unpack. BPP black box, that's a term from a paper of Gutfreund, Schofield, and Toshma. It's like a class-specific black box reduction. So it's only guaranteed to work if the oracle actually belongs to the class that you're talking about. So in this case, the oracle needs to be a PPT algorithm. And then search version means that the oracle does actually need to give the reduction like a somewhat good circuit for the distribution. And I don't have time to say much here, but just to give you like a little bit of intuition for the first direction, we kind of do things this way to really force that the circuit violating witness encryption was constructed uniformly. Okay, the reduction only needs to work if the oracle is a PPT algorithm, so we can assume that it is, and we assume that it gave us a circuit that's doing too well. That's a little bit of the idea. Okay, so I've talked about two types of reduction to PAC learning from that ABX paper. But here's a third kind that you might think about. And this type of reduction is sort of making like fuller use of the capacities of a true PAC learner. Okay, like for example, if you give a PAC learner exponential time, it should be able to learn exponential size concept classes with respect to the input length of the strings. It should also be able to learn over inefficiently sampleable distributions. Right, so one thing I could do is ask, if I'm a reduction, I can ask the learning oracle to learn over a target function defined on log length inputs. Okay, and then if I want, I could just then give it the entire truth table of the function I want it to learn. And that's also nice because now we can accommodate learners that require membership queries. I can also just give it the distribution I want it to learn over, maybe like represented as a table, poly-sized table. Yeah, we can call this reduction to learning in the exponential regime. Okay, but this should all be doable in polytime. That's a sort of reduction. And this is kind of analogous to the first type of reduction from ABX because the oracle is giving us back a hypothesis. But what if we wanted a kind of like decisional version of this one that's analogous to reduction to CGL? Yeah.
Can you just think of this as like MCSP for everything?
No, you skipped me. You skipped my next slide. Yes, exactly. Yeah, so MCSP is in this talk. What we get is just basically MCSP. Yeah, because what are we doing? We're just given a truth table and we're asking if there's a small circuit consistent with it or not. Okay, so in the yes case, it really, it is just yes instances of MCSP, but there are gonna be some more gaps, like we're generalizing to this learning setting a little bit. So, even for bigger circuits, they can only get small advantage, and it's gonna be in terms of the distribution that we gave.
I haven't seen like a distributional MCSP before. Is this the first time to your knowledge that it appears somewhere?
Average MCSP.
Yeah,
It's
there's,
in
yeah,
her paper, like,
What, really? With an explicit distribution?
well, maybe not, you know, I think we were using that uniform.
Yeah, we were using uniform with an explicit distribution given as a table that the algorithm is supposed to like deal with somehow.
It's like a natural generalization.
No, it's a supernatural generalization.
Assumes whatsoever.
Yeah. Anyway.
okay, so yeah, it turns out that that sort of exponential regime, MCSP, sort of learning NP-hardness under half-level reduction is equivalent to witness encryption, where the ciphertexts only have logarithmic length, with like corresponding parameters, in addition to a circuit lower bound for E. Okay, so just a couple of words about where the circuit lower bound thing is coming from. Well, in one direction, in order to go from this to this, we need the circuit lower bound to ensure that we can actually output a truth table of a function. Because that construction I gave earlier from witness encryption to construct a sampler, it's not guaranteed that that's going to be a function. You know, there could be in the support of the sampler, same string associated with 1 and 0. But by correctness of witness encryption, that can only happen in the no case. Okay, and because we're talking now about logarithmic length inputs, we can just check whether that happens. And if it does happen that we haven't produced a truth table, then we can just output this function, okay? And that's gonna be a no instance of this problem. And on the other direction, how do we get a circuit lower bound from this NP-hardness thing? That's an argument from Cabinet's and Psi paper. So just using the fact that this reduction is deterministic, we can take a trivial no instance of SAT, put it through the reduction, and what we get is the truth table of a function in E that doesn't have small circuits. Okay, that's the idea.
The initial reduction, right, so.
Yeah.
You wanted it to be an initial
It
reduction.
is, yeah, in this case.
Okay, so those are sort of like witness encryption and NP-hardness of
I
the.
take it back, so maybe a naive question, so maybe this witness encryption, basically this starts in a single bit and then you can like stretch it to 40 or whatever, so. I'm just wondering if you can stretch the log. It's an out, sort of an understanding, but I just wondered, you can do some kind of a trick like that.
Yeah,
Stretch it somehow.
I mean, you don't want to stretch it. It's stronger to have shorter.
So that's the same, if you like, speaking from the lower bound perspective, you can stretch it, you can do more things, so like there are more things that you're not supposed to, right? Exactly, you don't want to stretch it, but if you put pressure, what would happen, right? Does that make sense?
So you have an input message that is given to you and it's just only one bit.
Yes.
And then you have a length of the encryption of this message, which we want to get short as possible.
Yeah.
So log is like the strongest assumption. You want. But you don't want to have long.
Okay, the question is, okay, let's see. You don't want, but can you get it
No.
If it's longer than this, then you get something else for different related problem.
Okay, so yeah, that's it for like the characterizations of witness encryption by NP-hardness of learning. So we can kind of like complement that a little bit by trying to actually get some better NP-hardness of learning. So we can say a couple of things there. So there's the paper from Shuichi Hirahara, where he proves NP-hardness of MCSP star. The other main result in that paper is that it's NP-hard to agnostically learn programs in this kind of semi-proper setting, learning programs of size S by programs of size S times something. And I think it's also implicit in that paper that it's NP-hard to learn circuits of size S by circuits of size S times something a little bit smaller. So yeah, like on the one hand, this is kind of this like standard PAC learning of circuits setting, but on the other hand up here, you can get a bigger gap, which is better. It wasn't clear whether this could also be achieved for circuits. But okay, yeah, that's what we can do. Get the same like bigger gap, but for PAC learning circuits. But I won't claim to have done very much work to do this because really kind of there was just one missing like technical ingredient that was resolved for us in this paper from CCC last year, Holmgren and Rothblum. And they just give some kind of a circuit upper bound for this multi-selection problem. It's like a multiplexing kind of thing. So if you have a string of length n and you want to pull out q indices from it, the circuit required to do that isn't too much bigger than linear in n plus q. Okay, so I won't go into any detail, but that's just what allowed us to construct a circuit in the completeness case of Shuichi's argument. So yeah, something worth stating. We can also get NP-hardness of learning in a setting that's like basically almost improper, but it's learning in this like Oracle PAC model that we define here. So what is Oracle PAC learning? The idea is that the PAC learner is given as input explicitly a polynomial length string O, representing the truth table of an oracle. And then it needs to learn, it just needs to learn with respect to poly-size oracle circuits. Okay, and the nice thing here, it doesn't need to work in the worst case over those oracle strings. It doesn't need to work for any string, but just with high probability over efficiently sampled strings. Okay, and this is building on a framework from a paper of Wang, Yalongo, and Ren, where they show that there's a distribution in PSAMP, where with high probability over oracles sampled from that distribution, witness encryption exists in that oracle world. So then this is just kind of a consequence of our main connections. We take that witness encryption in the oracle world and turn it into NP-hardness of learning, and this is the NP-hard model of learning that falls out of that. I'm like definitely running out of time, so I won't say much about this, but some kind of like implications for ruling out some of Impaviazzo's worlds given these types of NP-hardness. So some like improvement to the theorem from ABX that if the learning is NP-hard in this first sense, then we can get all the way from worst case hardness of NP to one-way functions. So heuristica in addition to Pessyland. And then if learning is NP-hard in the second more restrictive sense, and I'm also like sneaking in that it has to be a half-Levin reduction, then you can get all the way to public key encryption. So you can also exclude mini-crypt. And then, yeah, so the title of my talk was Toward Witness Encryption via NP-hardness of learning, or something like that. Okay, so this is I'll admit this kind of my motivation with all this. I think it would be really nice if we could take some, my hands up, okay. Take some of these like very powerful and like even non-relativizing amazing techniques that are used to get NP-hardness and use them to get some kind of non-trivial forms of witness encryption unconditionally. Okay, and I believe that given known NP-hardness, we actually can get some non-trivial witness encryption unconditionally. And I put a question mark beside non-trivial because how can I prove it's non-trivial? I just haven't thought of another obvious way to do it. But the point is that Shuichi's reduction to agnostic learning is in fact a half-Levin reduction to CGL. Okay, it is randomized, so you need to be careful with that. But one thing you can do, just inspecting the proof and kind of pulling out the randomness and treating it as an oracle, you can come up with polytime algorithms and DEC, and they have shared access to a uniformly random string of super polynomial length, and then they'll be secure against arbitrary poly-size circuits. Okay, so that's nice, but it's a little bit unsatisfactory because I don't see how to give the adversaries access to the same random oracle. And then you can compare it with the result from HIR, and for a different distribution, they get witness encryption, and everybody gets access to those oracles. So I think there's an open question there. And then just one more open question is, can we use some NP-hardness of PAC learning restricted circuit classes or MCSP versions of restricted circuit classes and get some witness encryption secure against some restricted circuit classes?
Yeah, it's really hard to parse your last slide, but it's just something like there is secure witness encryption in the random oracle model for private key encryption, private key witness encryption.
Oh, what is private key witness?
So that's what we're trying to make up. But say that the person doing the decryption and the person doing the encryption share a small private key. And then you want to be, it's definitely like, if they have a witness, any statement, they can decrypt. And if something's not in the language, then an attacker that doesn't know the private key cannot distinguish. So it's kind of asymmetric between the legitimate parties not only know a witness, but have a private key, and the illegitimate, the attackers don't have a private key. And I'm just making this up. But
That's probably something like what I'm saying. Yeah.
And the account, not a symmetry.
yeah, so we have the correctness is for a decryptor who not only knows the witness, but has a private key. Okay, knows the private key. And the soundness is for an attacker for statements that are definitely not true, and the attacker doesn't know the private key.
What's the private key here? Is it a witness?
Well, so it'd be like so you're saying like it would be in the random oracle model, you want to like compress the access to that oracle part as like a key to like AES or something like that.
I see.
Some hash function that's in a random word that we view as a random word. Kind of just like match your words to other words. It's not, I don't think I have any content.
So much.